Scientists already know how to describe an orbital ring on paper: a moving mass stream, magnetic support, a road in the sky held up by momentum instead of stone. The harder question may be far less elegant. Can anything that large survive the junkyard humanity is building around Earth? In the year 12,043, the Future Archives catalogued Meridian Rail, a 14.2-meter curved transit segment, impact-pitted, heat-darkened, and patched so many times its repairs outnumber its original panels. One inscription survived in the guideway wall: "Clear corridor before lift cycle." That changes the mystery, because the first orbital ring may not have failed, or endured, as a triumph of materials science alone. It may have been built in open argument with Kessler Syndrome itself. To understand what this records, we have to go back, not to the far future, but to a paper from 1978. Donald Kessler and Bertincourt Palais described a problem that sounds almost trivial at first. Put enough objects in orbit, let a few collide, and each collision creates fragments that can strike something else. The number of impacts rises. The number of fragments rises with it. Eventually, debris can increase faster than nature removes it. That is Kessler Syndrome. Not one explosion, not one apocalyptic moment, but a statistical trap. Low Earth orbit is not empty space. It is a layered traffic system. Some objects are large enough to track from the ground, and agencies like NASA and ESA follow tens of thousands of them. But the more dangerous truth is that much smaller fragments, too small to monitor one by one, are vastly more numerous. A paint chip-sized particle at orbital speed can hit with the energy of a bullet. A centimeter-scale fragment can cripple a satellite. So, the scientific question behind Meridian Rail is suddenly sharper than it first appears. An orbital ring is supposed to be a permanent transport structure wrapped around a planet. But permanence in low orbit is exactly what the debris problem punishes. Before anyone asks whether humanity could build a ring, the first question is whether Earth orbit is becoming the kind of place where large, long-lived structures are punished for simply existing. The reason this matters is speed. Objects in low Earth orbit do not drift past each other gently. Relative collision speeds can reach many kilometers per second. At those velocities, impact energy scales so brutally that tiny fragments become spacecraft killers. Engineers do not just worry about hitting another intact satellite. They worry about the invisible shrapnel field left behind after earlier mistakes. And those mistakes are not hypothetical. In 2007, the destruction of the Fengyun-1C satellite created one of the worst debris events in orbital history. In 2009, Iridium-33 and Cosmos 2251 collided by accident, producing another major cloud. Those events mattered because they happened inside already useful orbital bands. They did not simply add clutter. They altered the environment future spacecraft had to cross. This is one of the least intuitive facts in modern spaceflight. Orbit is not ruined by weight. It is ruined by velocity and persistence. A dead satellite can remain dangerous for years or decades depending on altitude. A fragment only a few millimeters across may never be tracked individually, yet still force shielding, maneuvers, redesign, and mission risk onto everything nearby. That is why the engraved warning on Meridian Rail feels so revealing. Clear corridor before lift cycle. Not ceremonial language, operational language. Whoever built that structure was not treating debris as background noise. They were treating it as traffic, weather, and structural hazard all at once. So, where does the ring idea come from? In 1982, Paul Birch described an orbital ring that is often misunderstood in a very specific way. People imagine a giant rigid hoop encircling Earth, as if the challenge were simply finding a material strong enough to hold itself up. That is not the concept. A true orbital ring is dynamically supported. The central idea is that a mass stream races around the planet inside a sheath. Electromagnetic systems transfer momentum from that moving mass to a stationary outer structure. In principle, that lets part of the structure remain fixed relative to the ground, suspended above the atmosphere without depending on impossible compressive strength. That distinction matters. A ring is less like a bridge and more like a machine that never gets to turn off. If the mass stream slows, if guidance drifts, if power fails, if thermal expansion pushes the geometry out of tolerance, the structure does not simply sag a little. It enters a control problem. Energy, sensing, magnetic support, and continuous correction are not enhancements. They are the structure. This is the first major scientific correction the artifact forces on us. Meridian Rail contains superconducting guideway traces and actuator housings because the ring was never going to be passive. It had to be actively held in its designed shape every moment it existed. In other words, building an orbital ring is not mainly asking whether materials are strong enough. It is asking whether civilization can run a planet-scale feedback system in an impact-rich environment without losing control. At first glance, that sounds discouraging, but another part of the equation has changed dramatically in the early space age of the 21st century: launch cost. For most of the 20th century, many megastructure ideas were defeated before engineering even began because lifting mass into orbit was too expensive to discuss seriously. Reusable launch systems changed that calculation. They did not make orbit cheap in any ordinary sense, but they did shift the conversation from impossible to industrial. That matters because an orbital ring is not a one-launch project. It is millions of parts, maintenance stock, power hardware, guidance systems, fabrication tools, spare modules, shielding, robotics, and probably an entire construction economy in orbit before the final system resembles a ring at all. So, one genuine opening appears here. The same launch revolution that crowded low Earth orbit with satellites also made large-scale orbital construction easier to imagine. That is the paradox at the center of this episode. Humanity is becoming more capable of building an orbit at the same moment orbit is becoming more hazardous to build in. And there is a second twist. The technologies an orbital ring would need: autonomous inspection, precision rendezvous, in-space repair, traffic coordination, overlap heavily with the technologies needed to manage debris, which suggests a possibility worth taking seriously. The road to a ring may begin not with the ring itself, but with mastering orbital sanitation as a permanent industrial service. That brings us to the central engineering conflict. Where would such a ring actually go? If engineers place it in or across common low Earth orbit traffic bands, access from Earth becomes easier, tethers are shorter, cargo climbs are less punishing, communications delay is lower, but the structure also becomes a vast collision cross-section, laid across one of the busiest regions humans have ever used. This is not just a question of one impact on one beam. A ring would create repeated trajectories, known corridors, and permanent infrastructure that other spacecraft must avoid. Every operational satellite, every derelict body, every fragment cloud, every military asset, every launch window starts to matter. The problem stops being purely mechanical and becomes geopolitical. The alternative is to go higher. A ring above the densest operational debris bands could reduce random impact exposure from crowded low orbit. That sounds safer, until the penalties arrive. Longer tethers become harder to stabilize. Radiation exposure grows more severe. Climber journeys take longer. Power delivery and rescue margins worsen. You may solve one risk by buying 3 new ones. This is why no one should talk about an orbital ring as though it were one invention. It is a bundle of coupled decisions: altitude, traffic law, debris cleanup rate, repair strategy, and failure tolerance. And each choice changes what kind of artifact a future archive would recover from the sky. Present-day policy already hints at how serious this has become. When regulators push operators to dispose of dead satellites faster, as in the FCC's 5-year post-mission disposal rule for many low Earth orbit missions, they are acknowledging a simple fact. Space sustainability is no longer a polite guideline. It is becoming a design constraint. Yet cleanup remains primitive compared with the scale of the problem. Active debris removal has been demonstrated only in early forms. A mission can target one object, maybe prove rendezvous and capture, maybe deorbit a derelict. That is valuable. It is not the same as cleaning an orbital ecosystem containing countless hazards spread across altitudes, inclinations, and ownership regimes. This is the quiet lesson hidden inside Meridian Rail's patch skin. The repeated repairs suggest that even after construction, maintenance never ended. The first practical ring may have depended on an orbit-wide workforce of trackers, tugs, inspectors, and autonomous patch systems just to remain operational. So, the most credible near-term path is not build first and tidy up later. It is build the cleanup machinery, the governance, and the traffic discipline that make a ring survivable at all. If you've enjoyed this investigation so far, subscribe to future archives. There's another recovered mystery waiting. From here, 3 serious futures begin to separate. The first is cleanup first, ring later. In this path, governments and commercial operators accept that no planet-scale structure belongs in crowded orbital lanes until debris removal becomes routine infrastructure. Decades are spent clearing dead spacecraft, enforcing disposal, and carving protected corridors through the most useful shells. Only then does a partial cargo ring appear. It is not elegant, it is redundant, scarred, and maintenance-heavy. But it works because sanitation came first. The second path is more aggressive, build through the storm. Falling launch costs and better robotics tempt engineers to start early, before orbit is truly clean. The ring is armored, compartmentalized, and constantly repaired. Predictive tracking and local decoupling systems limit damage. In that future, the ring survives by becoming the largest debris management machine ever built. The third path is failure without scientific failure. Ring physics remains sound. Humanity simply never secures the orbital environment needed to justify a vulnerable megastructure near Earth. Cleanup lags. Insurers resist. Military operators refuse exclusion corridors. Safer alternatives win. Notice what these futures share. None of them are decided by a single miracle material. They are decided by operations, which is exactly what the scar patterns on Meridian Rail have been trying to tell us from the start. By this point, one conclusion is already defensible from present-day evidence. An orbital ring is not best understood as a monument in space. It is infrastructure embedded inside another infrastructure, the orbital environment itself, and that means the real prerequisite may be civilizational rather than mechanical. Humanity would need to do several hard things at once: track far more objects, remove derelicts at scale, coordinate launch windows internationally, define exclusion corridors that powerful actors actually respect, build autonomous maintenance systems that can inspect, patch, and isolate damage before local failure spreads. Then, on top of all that, sustain a moving mass stream and magnetic support network with extraordinary reliability. That sounds daunting because it is, but it is also clarifying. The ring does not wait at the end of a single invention. It waits at the convergence of debris, science, governance, launch economics, in-space industry, and control theory. So, when the archive records a patched rail segment rather than a pristine symbol, it may be preserving the most honest image of the first ring ever built. Not a perfect circle descending from genius, but an endlessly repaired machine operating in a sky humanity had finally learned, barely, to manage. And that leaves the next question exactly where it should be. Not can the equations close, but which bottleneck breaks first, the machine or the orbital commons it depends on. The obvious escape is altitude. If low Earth orbit is crowded, then move the ring higher, above the busiest shells, above the densest traffic, above the most persistent swarms of mission-killing fragments. That idea is grounded in a real engineering trade. A higher structure would likely see fewer random encounters with the specific debris populations created by congested low-altitude operations. But the gain is not free. Every kilometer upward makes access harder. Tethers become longer. Transit times increase. Loads grow more difficult to damp. Radiation exposure changes. Power delivery becomes more demanding. The machine may avoid one hazard by inheriting 3 others. And there is a deeper point here. Orbital rings are not useful because they merely exist. They are useful because cargo and people can reach them repeatedly, cheaply, and safely. Raise the ring too high, and the transportation system attached to it begins to dominate the problem. The ring stops being the shortcut and starts becoming another destination that requires its own expensive infrastructure. This is why altitude is still an open scientific question, not a solved one. Engineers would have to balance debris density, atmospheric drag, launch energy, tether geometry, radiation environment, and failure consequences all at once. There may be no perfect shell around Earth, only a least bad one. That matters for Meridian Rail. Its guideway spacing and actuator housings suggest frequent traffic, not a ceremonial installation. Whatever larger system it belonged to was built where access mattered, which hints that the builders may not have fled the orbital mess entirely. They may have chosen to work near it and manage it. That leads to the harshest competing theory. Perhaps humanity never needed to clean orbit first. Perhaps it only needed to build a ring that could take a beating. This is the armor and autonomy argument. In present-day spacecraft design, survival often comes from layers of defense rather than perfect avoidance. Shielding can stop tiny particles. Compartments can isolate damage. Redundant electronics can ride through failures. Sensors can detect degradation before it becomes fatal. Scale that philosophy up far enough, and the first ring starts to look less like a bridge and more like a continuously healing organism. The patch plates on Meridian Rail fit that logic disturbingly well. They imply planned replacement cycles. The mismatched alloys imply repairs made at different times under different constraints. The burn patterns around local housings suggest repeated intervention near active control hardware. This is not what a one-and-done monument looks like. It is what a machine looks like when maintenance is part of its design language. There is a real scientific precedent for this way of thinking. Hypervelocity impacts are governed less by the bullet image we imagine on Earth than by energy density. Even a tiny fragment moving at orbital speeds can pit surfaces, spall coatings, or damage exposed systems. So a practical megastructure would not be designed around never being hit. It would be designed around expected impact rates, tolerated damage states, and repair times. But this path has a limit. Local damage is survivable only if local failure does not trigger global instability. For a dynamically supported ring, that is not a small assumption. And that is where the debate hardens. An orbital ring is dynamically supported. That phrase sounds elegant until you ask what happens when elegance is interrupted. The central concept, going back to Paul Birch's analysis, is not a rigid hoop hanging in the sky. It is a system held up by motion, electromagnetic support, and active control. That means disturbances are not just dense in metal. They can become errors in alignment, timing, and load distribution. A useful comparison comes from power grids and high-speed rail. In both, a single local fault can sometimes be contained, but under the wrong conditions, it can also propagate, because every part of the system is coupled to every other through flows of energy and timing constraints. A ring would couple those flows on a planetary scale. So the question becomes extremely specific. Could one damaged guideway segment be isolated fast enough? Could a carriage lane decouple before an impact-induced wobble reached neighboring nodes? Could the moving mass stream remain stable while support housings were replaced? These are control theory questions as much as materials questions. This is one reason no present-day hardware can be treated as a miniature proof. We have maglev systems, we have superconducting components, we have autonomous docking, we have orbital tracking networks. What we do not have is one machine combining all of them continuously, globally, under bombardment, with failure consequences measured in continents. The burned field coil diagram, preserved on Meridian Rail, matters here. It tells us the ancient builders did not trust passive strength alone. They relied on active stabilization at the local level, which means they must also have faced the nightmare every controls engineer knows: small errors that do not stay small. That is why many engineers would expect a partial system first, not a complete circle around Earth, not on the first attempt. The most plausible early architecture may have been an arc, an equatorial freight segment, a mass stream test loop, or a hybrid system linked to tethers and launch assist infrastructure. That would lower the immediate scale, limit the consequences of failure, and let builders learn how real debris, thermal cycling, electromagnetic noise, and maintenance delays behave outside simulation. This is how large technological systems usually arrive, not as perfect final forms, but as narrow-use corridors. Railroads began as freight lines before passenger networks. Electrical grids began as local systems before they were continental. Even today's reusable launch systems did not start with full industrial cadence. They earned it by repetition. A partial orbital ring would also answer a practical economic question. What pays for the thing before it transforms civilization? Cargo does, propellant does, bulk materials do. If the first arc sharply lowered the cost of lifting mass to orbit along one corridor, that corridor could finance its own expansion. And now, Meridian Rail becomes more legible. Its curvature proves a larger parent structure, but not necessarily a full globe-spanning ring at the moment this segment failed. Its heavy wear suggests throughput. Its repeated replacement plates suggest root value. This may not be a relic of completion. It may be a relic of transition, from test article to indispensable infrastructure. And that distinction changes which future looks most plausible. By this point, 3 serious futures remain. The first is cleanup first, ring later. In that path, orbital sanitation becomes civil infrastructure. Debris removal fleets, disposal rules, traffic coordination, and protected equatorial corridors mature before major ring assembly begins. It is slow, expensive, politically difficult, but it reduces the chance that construction itself amplifies the hazard. The second is build through the storm. Cheap launch and capable robotics make delay look wasteful. So construction begins while orbit is only partially stabilized. The ring survives by brute maintenance, shielding, tracking, replacement modules, and autonomous repair. In that world, the ring is built earlier, but it never stops fighting for its life. The third is, debris wins the race, not because orbital ring physics fails, but because institutions do. Launch traffic grows faster than cleanup. Insurers price risk upward. Military operators resist exclusion zones. Commercial constellations occupy the most useful corridors. Humanity chooses lunar industry, high-altitude alternatives, or non-ring launch systems instead. Notice what has disappeared from the center of the argument. Not strength of steel, not one miracle fiber, not one cinematic invention. The bottleneck is whether near-Earth space can be governed as shared infrastructure. That conclusion is not fiction. It follows directly from present-day evidence. Collision cascades are real. Smaller fragments outnumber the trackable ones. Disposal compliance already matters. And active debris removal is still nowhere near industrial scale. So, when people ask whether humanity could build a road around Earth, the sharper question is whether humanity can first behave as though Earth orbit is a road system, not a dumping ground. At this stage, the archive object can be read more carefully. Meridian Rail does not prove that humanity built the ideal orbital ring imagined in early theory. It does not prove the ring was global. It does not prove it was permanent. And it does not prove the debris problem was solved. What it does prove is subtler, and in some ways more important. Someone built a transit structure attached to a dynamically supported orbital architecture. Someone expected repeated lift cycles. Someone operated it in an environment dangerous enough that warning pictograms about intersecting trajectories had to be embedded directly into the hardware. Someone repaired it often enough that maintenance marks accumulated in different alloys across generations. That is extraordinary evidence. It means at least one civilization-scale attempt crossed the line from concept art to operations. The ring was not only thinkable, it was serviceable, inspectable, patchable, burdened by routines. In engineering history, that is the moment when a machine becomes real. Not when the prototype works once, but when crews write procedures for the failure modes they now consider normal. The inscription translated as clear corridor before lift cycle may be the most revealing line on the entire fragment. It does not celebrate triumph, it describes protocol. And protocol appears only after a danger becomes familiar. So, the artifact's scars are not embarrassing leftovers on an otherwise glorious machine. They are the explanation. They suggest the first practical ring was inseparable from the debris clearing, traffic control, and repair ecosystem built around it. So, which future best fits the evidence? Based on what we can measure today, the strongest path is not a pristine ring descending after one breakthrough. It is a layered public works project. First come tighter disposal rules, better tracking, and cheap enough launch to support large service fleets. Then come debris removal campaigns targeted not at all of space, but at the corridor's construction and lift cycles would actually need. Then come partial freight arcs, heavily instrumented and absurdly redundant. Only after that does expansion towards something recognizably ring-like become credible. This is informed speculation, not established history. No present-day institution has yet demonstrated cleanup at the necessary scale. No ring control architecture has been proven in orbit. No autonomous repair system has shown it can maintain a planetary transport line for decades. But this path asks for the fewest miracles. It treats each impossible-sounding requirement as a version of something already visible in embryo. Conjunction management, reusable-launch, robotic servicing, phased infrastructure, and active control. It also matches the psychology encoded in Meridian Rail. Patch the damage, replace the plate, clear the corridor, run the lift cycle again. That is the mindset of builders who solve the problem operationally, not elegantly. If this interpretation is right, the first orbital ring was never just a structure above Earth. It was the machine that forced humanity to become competent at living around Earth. And that may be the larger scientific consequence preserved in this wreckage. And yet, the strongest competing view remains powerful. Critics would argue that this interpretation gives too much credit to maintenance and too little weight to scale. A planet-spanning structure presents a collision cross-section unlike any spacecraft fleet. A single badly modeled fragment cloud, a software fault in distributed control, or a geopolitical breakdown in traffic coordination could turn a repairable system into a cascading one. In that view, Meridian Rail is not proof that humanity solved the orbital commons, only proof that it gambled on it. That is why the artifact matters so much. It narrows the future without closing the argument. The rail's scars tell us a ring-like system did operate. Its repairs tell us damage was routine. Its warnings tell us debris management was operationally central. But the same evidence leaves one essential question unresolved. Did continuous maintenance make the ring viable? Or did it merely postpone the consequences of building too soon? For the future archives, that is the real lesson. The challenge was never just to suspend a road above the planet. It was to build a civilization disciplined enough to keep that road clear. Meridian Rail is not the memory of a perfect machine. It is the memory of a species trying to deserve one. So here is the scientific debate worth carrying forward. If orbital ring physics is sound, is the true bottleneck the machine itself, or the cleanup and governance needed before the first segment ever rises? Let me know in the comments.